Welcome back to the hyperbolic. Okay. Welcome back to the hyperbolic coding chamber. We are live, unfortunately, and what that means is that we have to spend another day on this godforsaken website. But fortunately, we have some great words to guide us through the mist, guide us through the never-ending waterfall of tribulation, pain, destruction, and overall unpleasantness with the kind words from Island Eagle. Rory the Warrior and Roger the Warrior were reared wrongly in a rural brewery. I mean, it doesn't get much better than that. So, just a couple of words for you to live by today. So, yeah, just a couple of words to live your life by. So, if you're looking for some, just general, if you're just looking for a guiding light to mold your life, if you're looking for just a shape to mold your life by, you just want to do that. So great words. And yeah, then we have 15 explant, great video. So I would say is great human. So we're back once again. I've been thinking we're a little bit shorter on time today, so today's going to be like 50-minute, probably 48-minute. I was just doing some reading. Yeah, I think I might have figured out the waking up early, and this is pretty crazy because to wake up early, okay, it took me a long time to realize this. I'm realizing to wake up early, you just have to go to sleep earlier. So that could be the new wave. So, we might rename the Discord to the Hyperbolic Waking Chamber, just because that may be the greatest challenge. I thought it was LeetCode, but waking up early may be the greatest challenge man has ever had to face. But yeah, so I think if we could wake up earlier, do a nice 2-hour session, that would just be magnificent. That would be magnifique. But yeah, I don't know how to get there. I woke up at 8:30. I rolled around for like 45 minutes, and then I finally got up. It was like 9:15. Then I had to do some other stuff, just administrative stuff. Then it was like 9:40. Then I read for like 25 and did some review. And then now we're here. Ideally, would wake up at 8:30 and then immediately go from LeetCode to go to supplemental reading and then LeetCode, and then that would be dope. So I think one way that we can solve more problems, and I think John Carmack said this, there is definitely some diminishing gains on doing something a lot. Like if you're working on a program, you keep working at it, you run out of brain sauce. At some point, you're doing negative work. This is true, but depending on the nature of how you work and the work itself, sometimes working more is just better. So maybe we could go even further if we multiplied just how much time I was spending on this. So right now we're seem to be averaging around like 1 hour, between 45 minutes to an hour, which is okay. Imagine if we were averaging 2 hours. That means in the span of the time we would typically have done, for example, if in a month I do 30 hours, that would mean in a month we could do 60 hours. So that would be even crazier. Then if we do 3 hours a day, it would even go up to 90 hours. And then from there, it would just be a matter of time of waiting. That would be ideal. Those would be the ideal circumstantials, but I'm not certain. Also, I was thinking about streaming. Maybe you could do some streamed sessions. I think the plan would be that the session would be the same. I would still do my regular daily session on stream because I need some uninterrupted practice. Then you could do a lower, more autopilot session on stream. That could be cool. But yeah, I haven't figured out a way to make it work with the whole schedule because I'd like to be able to standardly do 2 hours a day. That way the streaming would not affect it. But I have no idea how that would work. It would probably have to be like just on the weekends when I have ample time. So, who knows? Who knows? But what I do know is I scream, you scream, we all scream for ice cream. So we're going to jump into it. I'm already running out of time, and I already have 48 minutes left. So yeah, I'm just going to jump into it so that we can get some good focus time in. So I'm going to jump into it. And we have some problems I think we're working on. Did we solve this problem already? Did I really submit this many wrong answers? I remember what we were doing on this. Oh yeah. This problem was strange. It was yeah, something was off about this problem. I can't remember what it is. First, we were pretty much doing a 3-pointer movement, front, mid, and end, and then for some reason there was a test failing. Oh yeah, when there's no segments and the string exists, and there's more than one segment. There were just a couple weird test cases. This problem has a massive number of dislikes. So I put 5 here and they wanted 6. 1, 2, 3. I see. Yeah, this problem is a little ghetto. I think we could 2-pointer this. Wait, this should say mid and no. Something just feels ghetto about this solution. I guess I could fuse these. It might just be easier to read if it's like this, actually. I think what we need to do instead is just count the words, I think is what they're looking for. So what we could do is we'll start, I have 2 pointers. We'll start the one at the front and we'll basically say iterate until you find a non-space character, which is here. And then the second one is going to start where the last one found it, right? And we're going to iterate until we find a space character. Then we'll count. And if we find the space character, then we'll set the other one. We'll set pointer 2 equal to pointer 1, and then we'll do the same thing again. And then this one we can just call it front and end. And change this 4. We'll say while front is less than s dot length. Do front plus equal 1, so we get to f. After that, we'll say end equals front. And then we'll say while s sub end does not equal through here, we're looking for the first space character. They actually want to swap these. So while s sub front equals space, we want to keep going forward because we're looking for the first character. So stop when we get to s. We swap the case here. End is going to equal to front. It's going to start at f. We want to go until end is equal to the first space character. So while it doesn't equal space, we're going to do end plus equal 1. Now we can say where'd my segments go? And then we'll have a segments variable, and then we'll just say front equals end. I'm not understanding. Why is this never ending? if we start at front equals 0, s sub front does not, s sub front equals space, it doesn't, so we're going to put front at index 0. Then we're going to set end equal to front plus 1 at index e. While s sub n does not equal space, which e does not, we're going to do n plus equals 1. Eventually it equals space. Oh no, well, no, yeah, s sub n, yeah, does not, and then eventually equals space. We do segments plus equals 1, and then we do front equals end plus 1. I see. I forgot to bound it, and end is less than s dot length. So it ends, front is less than s dot length. I thought I had to put an if case there. But now we want to say if s sub front not equal space and s sub n does equal space segments plus 1. But then when we go out of bounds, it doesn't count as a s sub front does equal space though. That's what I don't get. How are we outputting 1? Jeez, now I see why this one had so many dislikes. I guess maybe that's the issue when there's a lot of test cases, like when the test cases are really good. Maybe that's why problems have a lot of dislikes. Yeah, maybe that's when problems have a lot of dislikes. It's hard to know though. Or maybe they could have given us better examples. Because I think maybe the problems get a lot of dislikes when you literally just have to keep clicking run to find out the edge cases. Or maybe, oh, maybe that's why people say websites like Code Forces are harder, because they don't give you the edge cases. Maybe we're being held by LeetCode. Maybe we should stop looking at the test cases that are failing. Given the root of a binary tree, given the root of a binary tree, given the root of a binary tree, return the length of the diameter. The binary. Return the length of the diameter of the tree. The diameter of a binary tree of a binary tree is the length of the longest path between any two nodes in a tree. The diameter of a binary tree is the length, the longest path this path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges. Diameter of a binary tree is the length of the longest. Diameter of a binary tree is the length of the longest path between any two nodes. It's just the length of the longest path in the tree, I guess. So I guess there would be 2, which could be multiple lines. Oh, whoa, 3. Oh, yeah, you can go through the root. 1, 2, 3. I feel like you could just do a DFS and then add the numbers together. So if we did a DFS here, you just add 1 whenever we go deeper. Start with 0 here, except we do these two nodes separately. So we do DFS starting here from 2, do 1 to both of these, and then 1. And then we could just return the depth, the largest depth. So think about it. Start from 2. We can return the math.max of depth of left and right, and a 1 plus math.max. So we go deeper, add 1. And we'd add 1 right on the outside, so that's fine. Deeper. Then when you're coming back up, we're returning the max of the 2. So I think this could work. So I think you can probably just use the function definition they've already given us. Otherwise, we'll return 0, and it's going to return a number. Oh, I said root. We can just change this to node. Node has to exist. If it doesn't, we don't count it as an edge. So let's just run it through real quick. We'll call it with 1. Right, and we're going to return 1 plus the math.max of diameter of the left. And I actually don't think you can do this because you need tree node or null. Place this in here. I can't see how you split this up because then you'd need to do depth of node dot left, or call it max depth plus max depth of node dot right, and we can change the function name to max depth. So we'd start at 2. We'd say, okay, the node does exist, so return 1 plus the math.max of max depth left. So go here to left. We add 1. I feel like I know how to code this, but I want to, and I feel like I could just code it, but I feel like I need to actually I feel like I need to be able to visualize it in my head. But I feel like we could just code the solution, but I want to get out of the habit of just coding it and just stay out of autopilot. And the node 1. So we have access to, we're going to do node dot left. One plus math.max of max depth node one plus the math.max of I think the one on the outside adds it all up together. So you go to 4, we do 1 plus math.max of, well, there's nothing to add, so we end up returning 1. End up returning 1 for that one too. The max ends up being 1. We add 2 to it. And we would return that. V3. So maybe this does work. Oh, one of the last ones. Output was 7, the expected was 8. I wonder why I was like that. I feel like part of the issue is we're counting nodes, not edges. Hmm. Hmm. Seems like they're not counting too much. We're counting too little. So what scenario would we produce? The answer here for case 1 is 4. What if the issue is when there's this is the path. If we remove 3, I think I'm definitely misunderstanding this problem. Return the length of the diameter. The diameter of a binary tree is the length of the longest path between any two nodes. The longest path has to include jumping into the other side of a tree. It has to include both sides of the tree. So if we just get the depth, the deepest depth for both sides of the tree, then even now I'm not seeing how this would lead. Oh. Wait, no. How are we getting 8? Now that I'm thinking about this, how are we even getting 7? Oh, wait, no. It's not showing me the whole tree. I see now. 4, 5, 6. 1, 2. One, two, three. Two, three, 4. 1, 2, 3. Yeah, what's the path that gets you 8 here? 1, 2, 3, 4, 5, 6, 7, 8. I see where we messed up. Yeah, I think we assume. Okay, yeah, we assumed that. We assumed that. Yeah, we assumed that the longest path would always be going from one side of the tree to the other, when it's not exactly true. The longest path could be different, and it's these last cases that really test that, surprisingly. So this solution definitely is not going to work. I think a new solution that would be better. We just treat the I think we could do this in n squared. There's definitely a version of this I think you could do in n cubed, which is a little ghetto, but I think you could just treat the tree as a graph and then do a BFS on every node. BFS, pretty much linear time, but our version is n squared, but linear time. Yeah, that would get, I think, yeah, if we could do, yeah, if we did BFS on every node. If we did a BFS on every node, then we could just take the node with, sounds ghetto, but the deepest depth, basically. So the one issue with that is that we have a tree and not a graph. And while we can go downwards by visiting our children, We need to be able to go upwards as well to really be able to travel in all directions. So we're going to need to start would actually be a parent array. And if we had a parent array, then we could pretty much do this DFS for every node. I think the other issue we have is that are all the numbers in the tree this is another reason why JavaScript is a little bit dog. If there's any other language, we could just use the trees, the address of the node as a key, but in JS we cannot. But I think we could give each node a key automatically. Yeah, we'll just need a parent array. I think we'll just need a parent array, DFS on each node, return deepest depth. First, need the parent array. To get that, we could just do a BFS. Yeah, the parent array should be all that we need because given a node's ID, which is going to be its index, it'll give us the parent of that node. So let ID equal to 0, and we'll make parent an empty array of tree nodes. From here, we can make a function called collect parents, and we can just do a DFS, I think, and just pass in the parent node. So here we have a function collect parents. It's going to take a node, which is a tree node, or null, and it's not going to return anything. We have to make sure that the node does exist. Now we'll actually do something like this. We'll pass in the node's parent. Actually, do we need to pass in the node's parent? Or how is it a parent array? -1. I mean, wait, this is this is a little bit confusing, but we'll just call it node parent, tree node or null, and then we'll have parent, which is actually an array of tree nodes. If the node exists, we're pretty much just going to do collect parents, pass in node.left, parent, which would be the current node, and then the parent array. And we'll say if node parent, we'll say parent sub ID I have nodes as well, which is going to be an array of tree nodes. Parent sub ID equals ID plus equal 1. Or actually we can just do push. Parent dot push. The parent for this node is going to be node parent. And then we'll say nodes dot push node. Then we can print parent, and then we can also print the nodes. And then we minimize this. This is kind of making it hard to see. So we should be able to check this, but let's use a way simpler test case. I'll reset the test cases. Okay. Root's parent is null, okay. And 2's parent should have all of these nodes in it. And it looks like we're going, so 4's parent should have 2, 4, and 5. And then we should have 5's parent, we should have 2, 4, and 5 again. Then we should have 3's parent, which has 1, 2, 4, 1, 2, 3, 4, 5. So that makes sense. And then the individual nodes, right? Node ID with 1 is going to be 0. 2 is going to be 2, 4, 5. Oh, wait, I just realized we ran out of time. Oh, we can solve this one tomorrow. But yeah, I think, we just need to change it to the DFS. So I think this looks good so far, though.